So we're learning about solutions. Please take out your homework. I do have a little demonstration to show you here. My time now. So I'm going to take some 7-Up. Everybody know where they named 7-Up from? They used to use lithium as the flavoring for 7-Up. And the scientists thought they were being smart. No one's going to figure this out. Now, lithium was pulled from the flavoring of 7-Up years and years ago once they realized that lithium salts, were actually beneficial for treating mental health disorders. So they want to control that substance, not people self-treating themselves with 7-Up to get rid of depression or bipolar disorder. Okay, so lithium has atomic number what?
7.
No, atomic number 3. But its mass number is 7. I know, I set you up on that. So, 7-Up, of course, is a solution. The first drop is the same as the last. What's the solvent in 7-Up? No, sugar is not a solvent. Sugar is what's being dissolved. So water is the solvent. Sugar would happen to be one of the solutes. What other solute particles are in this? What are the ingredients that water is dissolving in here? Oh, what are the flavors possibly? What else is in here? What else do you see? Carbon dioxide. Okay, the fizz, is due to the carbonation. So we have CO2. This is a gas dissolved in a liquid. So there's CO2. Now notice something, party people. What's happening to the, what observations can you make here? Okay, it is kind of hard to see. Yeah, if you look carefully, you see that there's CO2 doing what? Can everyone see that you clearly have some bubbles or CO2 that is clearly leaving the solution, yes? Okay. So, the bubbles you see are due to the CO2 gas that's leaving. Now, what did I do to make the CO2 leave? What did I do? Right. Now, gas has tremendous energy. If I was well enough, I would say gas, because gas has tremendous energy, but I can't do gas because I'm not feeling well. Okay? Now, gas doesn't really want to be usually in a liquid because they have tremendous energy and have what kind of attractive forces do gases have if they're so free and can fly around the room hundreds of miles an hour? Weak attractive forces. So they're not going to stick to water very well. So, what could I do to stop this? What could I do? By me putting my hand over this. Okay, what will eventually happen? The bubbles will stop because what's happening is I'm building up the gas pressure. As the CO2 is leaving, okay, what I'm doing is the CO2 now is in the air, and the CO2 in the air, I'm increasing the pressure. I can actually feel my hand being pushed up. Now, as the gas builds up in here, what does it do to the gas bubbles on top? Is it going to make it harder for the gas to leave or easier as I do this? Harder. Okay, so what's happening for those that can see is the amount of bubbles have decreased or increased in the last minute. Everyone see that they've decreased? Okay, I'm going to remove my hand. But what's happening is the pressure is increasing. And as the pressure increases, the force on top of the liquid's going to do what? Increase. As gas leaves, think with me for a second. As gas leaves, all right, look at the bubbles here. As the gas leaves and builds up in here, bubbles are going to stop coming up. Do we see bubbles coming up when the soda bottle is stoppered? No, only when you take it off. So what's the difference? What just changed when you open the soda bottle? You release the pressure. Pressure in gas is a solubility factor. Now I'm going to remove my hand. Okay, for those that can't see, probably I got to turn this off. I'm going to remove my hand. See, you can see a difference. Okay, the pressure is building up. I probably don't have a perfect seal, but watch, I move my hand. Is there a difference? Let's see, let me pull it up to the top. I'm going to take away the light. Because I don't think it's, now we just changed all kinds of craziness. Okay? So I'm not sure what's happening here. But I'm going to do this, because that's not working out. Get rid of this. Okay? And let's turn this light off. Or let's turn this on. Okay, check this out. Everyone can see that what? The CO2 is leaving, correct? The CO2 is leaving. And I'm going to fill this all the way to the top. Now, so what I'm trying to show you today, party people, is that solubility can also be a gas and a liquid. And what we know is that I can control this solubility by increasing the pressure. Now, I can't increase the pressure myself, but if I put my hand over this, okay, let's try it again. Maybe with a little bit of space, I can stop this a little bit. What I'm trying to do is have the gas that's being released do what? Build up on top. If it builds up on top, just like I stop at a soda bottle, eventually the gas pressure will build up and prevent the gas from leaving. I think I see a difference already.
Yeah, I see it.
Okay? I think I see a difference. Now, I'm going to keep it on there for a couple more minutes. But, so when we talk about gases, their solubility depends upon temperature, as we talked about 2 days ago. But it's also dependent upon pressure. Okay? You open a soda bottle, the pressure decreases, and the solubility of the gas in the solution increases or decreases. What does that mean? If I open the soda bottle and I take my hand away, what's going to happen to the solubility? The ability of the water to keep the gas inside. Is it increase or decrease? Decrease. You lower the pressure, the force hitting on top of a gas. Okay, you lower that pressure, it's easy for the gas to leave. Now, it's going to take a while for this to stop, but let's see if I can remove my hand and see a difference. Okay, it's still not going to, I think it's slowing down good though. If I would be more patient, I could stop her this. In fact, if I had some ram wrap and some tape, I'd actually feel my hand pushing off. So here's what I'm going to do. Take my hand off and see if you can see a difference. It's definitely slowing down now. Everyone see that? Because what? We're getting to something called equilibrium. We're going to talk about that in the next unit. What's happening is the rate of bubbles leaving is equal to the bubbles coming back in. So eventually we'll get to equilibrium and there'll be nothing that looks like going on. So I'm definitely getting there. If you look at the bottom and going up, it looks slower. All right, what I'm going to make for you today is a fruit lava lamp. Okay? A cheap fruit lava lamp. Now the bubbles are clearly dissipating, aren't they? Now I'm going to remove my hand and hopefully we see a difference. If I could do this whole period, you'd be happy, right? Okay, what a great demo. We did watch bubbles stop. Okay, so yeah, keep it up. All right, so now I'm going to remove my hand. If I waited probably 5 more minutes, this would stop. I'm going to remove my hand. What's going to happen to the pressure? The pressure is going to decrease, and there's going to be less force pushing on the liquid. Therefore, the gas can leave easier. So hand comes off now. Was there an increase? A little bit, okay. I felt it on my hands. All right, in any case, let's add some more. Now, what I'm going to add now, as my demonstration is, I'm going to add a grape. So here comes my first object, the grape. Now the grape, whoa, the grape is floating. Why is the grape floating? What's happened to my grape? What's it have on top? What's collecting on the grapes? The bubbles, the CO2. So my friends in chemistry, the CO2 is attracted to the skin of the grape. My friends, let me ask you a question. What must be the polarity of the skin of a grape? Is it polar or non-polar? What dissolves what? What's the rule? Like dissolves like. So, what's the polarity of CO2? Is it polar or non-polar? Is it polar or non-polar? Like dissolves like. Look at CO2 for a second, right over here. CO2. CO2 looks like this, right? Is it symmetrical? Yes. Because of its symmetry, what? The CO2 bubbles that are collecting on this grape, this is a nonpolar molecule. So the skin of a grape must be what? Because like dissolves like. Now, it is flipping. Now what's supposed to happen is the CO2 is supposed to leave, but there's so much carbonation. Someone drop another one. Now why would it be a good idea for plants to make fruit with skins that have nonpolar skins? Well, if it rained out and you had a polar skin on your grape, if you had a polar skin on your grape, what would happen to your fruit? It would dissolve or just get big and expand. Okay? Strawberries don't have a real nonpolar skin. We don't peel strawberries, do you? So when you have strawberries in a big rainy season, they go bad fast because they absorb the water and they get big and expand. Grapes prevent that because they have a hydrophobic covering. They have a nonpolar covering. And CO2 being nonpolar is attracted to it. Now, I'm going to drop a peeled grape. Okay, now a peeled grape, okay, is just that. A peeled grape is a grape where I took the skin off. Now, it took a while to do that. Why did I do that? I did that. Well, it's not so much going to dissolve. By taking a nonpolar covering, CO2 has nothing to collect on. So it's just going to what? It's just going to sink. Now, I'm going to take some raisins. Now, what are raisins? I'm always fascinated. Yeah, but people don't know that. You say that like, oh my God, how can you ask that question? There's someone in here who doesn't know that raisins are dried grapes. See, there you go. Way to call her out. That's just so rude. Okay, now, I'm going to put grapes. Now the grapes, I'm sorry, these grapes have the skin on them. So they're going to attract the CO2. But because they're so light, okay, what's happening? What are we having? There's my fruit what? Yes, it's my fruit lava lamp. Now they're light enough, so what's happening, party people, is the CO2 is attracting, can't even see on that, the CO2 is actually attracting the what? Onto the skin. And it's making the raisins buoyant. So they float to the top. When they float to the top, what happens is they lose the CO2 and get heavier again. And we have our fruit lava lamp.
So cool.
Okay? So again, to look a little closer, why isn't the one without the skin working? It's got nothing for the CO2 to collect on. And as we go up, oh! Where'd they go? They're going to gain some what? CO2, and they get lighter. I got gas on me. Whoa, I don't know what I'm doing.
Oh, that's true.
It's tripping me out too because I don't know what I'm looking at. Oh, there's one going. Let's follow this guy. He gains more CO2. What's he do? Yeah, I'm going nuts doing this.
Yeah, it's really looks like a tube moving.
That's a horror movie right there. Okay, this is a bad shout out. Okay. All right. So in any case, there's our lava lamp. Okay, and it works because essentially of solubility, like dissolves like. Okay, and the ones going down don't have a lot of CO2 in them. The ones floating, CO2's on them. They get to the surface, they lose their gas bubbles, they go down, and this will go on and on until I lose enough CO2 or eventually the raisins get saturated. Okay? So that is our lava lamp.
How long would
fun.
it take for them to get saturated?
Probably half an hour. Okay? So let's continue on with our homework.
Mr. Grunsky,
Yes.
if you were to cover the top with all those raisins in now, would they sink? If they were,
If I cover the top,
if you were to cover the top
And
completely, and if it would just
yes. Because eventually there's no CO2 being exchanged anymore. That's my guess.
now, if you were to abruptly release that, would they all shoot up?
If you lost all the CO2,
No, I mean if they were just out of.
oh yeah, probably all float up because the CO2 is going to want to leave. Yeah, absolutely. Okay? All right. Just like when you shake a can and make all the little bubbles collect the big bubbles and they push out, we push the water out, this would push out the raisins. So I put raisins in here and shook it and opened it up and we're shooting out the water raisins. Okay. Okay. All right. So in any case, let's continue with the work of home. Okay. I'm going to start with this sheet here. Okay. And let's go to this. Okay. So when we go to table G, table Grodsky, I like to say, but they didn't want to put pay for the copyright and everything else. Here's my table G. Now, as I said to you before, solubility is the measure of how well the solvent, in this case water, will dissolve certain compounds. The action of the water on the solute particles. In my demonstration, the solute particles, okay, we're dealing with was CO2. And if you notice, CO2 does not like to stay in solution. It's leaving under low pressure. Notice these three lines, guys. Most of the lines are going up. You have to be aware of this. The lines that are going down are gases. Absolutely correct. Okay, you listened to my lecture, or you knew that. So this is a gas, this is a gas, and this is a gas. And you've got to know that gas's solubility decreases. Why does it decrease? There's less grams of them at higher temperatures. Think, if I was to heat up this soda, would the CO2 bubbles increase going up or decrease? Would they leave faster at a higher temperature? Yeah, it'd go flatter faster under warmer temperatures. Gases have tremendous energy. You give them more, they're going to leave the container. Has any of you heard of thermal pollution? If I have a factory that takes in a body of water, and I take in water, for instance, there's a nuclear power plant in our area, okay? In, well, not that far in upstate New York, but also in Connecticut, that takes water in, cools the reactor, pushes the hot water out. The sound can get warmer because of that. Now, it's a big body of water. Some people say it's not big enough to make a difference, but if the temperature of the water rises above normal, what happens to the dissolved oxygen that the fish and marine aquatic life need? It decreases, and their ability to sustain life decreases, and there have been instances where ponds or lakes or small bodies of water, because of an artificial increase in temperature by humans, have caused a deadly die-off of marine aquatic life because of a decrease in the amount of dissolved oxygen that the fish need. So it's something to think about. Global warming could impact the Earth's temperatures so that the water can no longer hold as much dissolved oxygen. So you've got to know that temperature decreases, and these are gases. The rest of these are solids. Okay, now how do we work this table? Christmas, what am I doing? I have this all set up. Okay, how do we work this table? Well, this table, okay, is very busy, and it's very hard to work with sometimes. So, I don't know, it's my attempt to try to make this easier. So the first question that I asked you to do last night, and if you didn't check the website, shame on you. You should be, okay? But rock on. Here's the first question. If 50 grams of water is saturated, the key word here is saturated. What does saturated mean? Yeah, saturated means on the line for this curve. Now, on the line means what? Because you're right, it means on the line, but it means something very special. It means that the solvent, in this case the water, is holding on to the what? Is dissolving as much of the potassium chlorate as possible at a certain temperature. So, at 23 degrees, that's about right here, okay, I have potassium chlorate. Now, potassium chlorate is KClO3, so it's right here. Now, I'm writing there because sometimes this graph gets so busy, people can't see what the easy answers are. Now, by saying that we're saturated, as someone just said, I think it was Cameron, it means that, maybe not, because you looked at me. Who was it? Jenny?
It was Lily.
Lily, as Lily said, in that general area, okay? Saturated means that we're on the line. Now, what does that mean?
It was Lily.
It means I'm holding on. The water is holding on to the max amount of water possible. Is slowly evaporated to dryness. Now, this means I have a solution with how many grams of potassium chlorate? How many grams of potassium chlorate? 10. I have 10 grams of potassium chlorate. Now hold on. In this graph, pay attention, party people, how many grams of water do I have? 100. What's the question saying? 50 grams. So listen to me, very important. 10 grams will saturate potassium chlorate at what? 23 degrees if I have 100 grams of water. If I have half as much water, don't I have half the ability to dissolve? So that you divide by 2, and the answer here is 5 grams. Now they said to evaporate to dryness. What they mean is, if I take 5 grams, now it's 10 on here, but that's based out of 100. So it's 50 grams, you have half this amount of water, you have half the amount. So the answer is 5 grams dissolves in what? 5 grams dissolves in 50 grams of water. Now if you boil off the water, like we did in the lab, you're left with the salt, you're left with the 5 grams. Remember the lab we boiled off the water using the evaporation dishes? Okay, so the answer is 5 grams. Any questions there? So when you do these questions, pay particular, what? Attention to how much water you have. Next question. What's the smallest amount of water required to dissolve completely 23 grams of ammonia chloride at 40? Now, the smallest mass of water would mean I probably should find out what the saturation point is. So, I want to dissolve 23 grams of ammonia chloride. So let's go find that curve. So I'm going to get rid of this. Maybe. And I have ammonia chloride now. And ammonia chloride is right here. Yeah, and as someone has mentioned, you have to know your names. So, what is the saturation point? Because they want to find out 23 grams of ammonia. I'm going to find my saturation point at 40 degrees, right here, and I'm going to do it for potassium chloride. And I noticed something. The saturation point on the line is right there. What does that mean? That means it takes approximately what? 40, let's guess 46. It takes 46 grams, right? What I'm doing is I'm just cross. These numbers here are how many grams of this substance mixed with 100. So in 100 grams of water, this entire graph is based on 100 grams of water. So in 100 grams of water, it takes 46 grams of ammonia chloride that will saturate the solution, meaning hold the maximum amount of ammonia chloride possible at 40. They want to find mass of water that will dissolve 23. Well, if 46 gets dissolved in 100, 23 would be dissolved in how much water? 50. So the answer is 50 grams of water will dissolve 23 grams. Because 100 grams of water dissolves 46. Okay? So the answer there is, I don't know, where's my, so I got 50 grams of water.
Where did you get 50?
Okay, 50 grams of water. Because they asked me, what's the minimum amount of water to dissolve 23 grams, I immediately went to my graph and say, what's the saturation point of ammonium chloride? And I said, and at that temperature of 40, it was 46 approximately, although it looks like it's moving on me. All right, probably a little lower. So 46 dissolves in 100, 23 dissolves in 50. Okay? Number 3. A saturated solution of ammonium nitrate in 100 grams of water at 40 is heated to 50. What's the rate of increase in solubility in grams per degree? It's an odd one, but definitely comes up. Okay, what just happened? Pulled stuff out. Well, that's not working. Okay, full of errors today. All right, so what is the rate of increase? Okay, from, what am I doing? Number 3. Heated from 40 to 50. What's the rate of increase in solubility in grams per degree? So sodium nitrate, let's go to the table. Okay, and from 40, what's the temperature here? 40 to 50, sodium nitrate. So here's sodium nitrate. Okay, so from 40 to 50. So if you look at the table, this is 10, 20, 30, 40. So I've got this value here, and this is 50. Okay, my friends in chemistry, how many grams is between here and here? That is what? How many grams between there, guys? 10, right. 10 grams. I didn't hear you, sorry. That's 10 grams. That's 10 grams here. So the change in what? Grams per Celsius degree. So it goes up 10. And what's the change here? From 40 to 50. 10. So what's the change of Y? 10 over the change of X. The temperature is 10. So what's the answer? Change of Y over the change of X. This is 10. This is 10. What's the answer? 10 divided by 10? Put in your calculator. So you got 1 gram per degree Celsius. It's just a slope. Okay, that's all that question was. An odd one, but we can do it. So the answer there is 1 gram per degree Celsius. Which salt is the least affected by changes in temperature? Guys, I don't want to talk over your voices. I don't. Which one's least affected by temperatures? When I say least affected, what do I mean? Which one is the steepest or the flattest? Yeah. Look at this. Sodium chloride. Kind of interesting. A salt that we take in our body. Is it a good thing it's flat? Salt in our body had a curve like this. Why is that detrimental? If we dissolve this like rock candy, let it cool, we would have what? If you're above the line, what do you have? If you're above the line, what do you have? Precipitation, solids coming out. So if you're at a fever, you eat some salty food, you would dissolve it. And as you cooled, you'd be above the line and precipitates would come out. Precipitation's not what you want, do you? So when you want a solid to form in your bloodstream, because we have a salt that doesn't change its temperature much, that's a good one to have in your body. Okay, moving forward. So sodium chloride's the answer there. Any questions? Any compliments? All right, let's jump around here. Number 7. What does precipitation mean? Can I ask you a question, Ms. Bava? Ask her help. If you go downstairs and you go through the doors, there's a beaker sitting there cooling to the right. Yeah, just walk with up carefully because any shaking it might precipitate. So that there's two doors. The doors to the left, it's cooling outside.
By the gym.
Yeah, just look to the right when you go to those two doors. If you could just gently bring those up. Now, I gave you some weird things to do. Okay, now, pay attention. Here comes this question. And this is another classic question. At 50 degrees Celsius, so here I am. All right? 100 grams of water is saturated with potassium nitrate. 100 grams of water is saturated. What does the saturated mean? It's on the line, maximum amount of potassium nitrate. So at 50, I'm saturated with potassium nitrate. Now, this is the 50 line. Potassium nitrate is going all the way up, so we're going to move this down. Can't do this backwards. Where's potassium nitrate? I can do this. Yeah, I can't do this backwards. Yeah, I might have done it. Okay, more or less. So here's potassium nitrate.
It's like this before I got home.
It was solid. Darn it. Okay, that's all right. It's okay, we'll put it down. I'll try again tomorrow with that. Okay.
And it's not totally solid.
It's done.
Alright.
All right, now.
That was my fault.
No, it wasn't. I'm saturated at 50 degrees Celsius, so 10, 20, 30, 40, 50. I'm saturated, so I am right here. Okay, now, how many grams will precipitate when it's cooled to 40? When it's cooled to 40, the saturation point is now here. But you put in this to saturate it. So how much am I above the line? How much am I above the line? That's 5. That's 10, and 5 more is what? So 20 grams comes out of the solution. 20 grams will precipitate. We call this a supersaturated solution. Okay? When you are above the line, I talked about this last night in the lecture for those that watched. If you have rock candy, okay? Let's look at rock candy for a second. You've heard of making rock candy, right? Here's the recipe. Take 2 cups of sugar and 1 cup of water. What you do is very simply is you heat the solution. As you heat the solution, what happens to the solubility of the sugar? It does what? Goes up. I can add more grams. This, of course, is grams on this side. This is temperature. Making rock candy is actually very dangerous because the soupy sugar solution is very hot, way above the boiling point of water. Now, you add a lot of sugar, 2 cups of sugar to 1 cup of water, and you're saturated. And what do? You let it cool. Now, the sugar that you added, whatever that is, that's not going to change. But the solubility drops. The ability of the water to keep it dissolved drops. And what you have is, once it gets to room temperature, this is how much precipitates out into a solid onto the string, let's say you hung below it or through it. And rock candy is made that way. Anytime you're above the line, it's going to come out. Now, there's a great little demonstration. I have to do another one tomorrow. But these are supersaturated solutions. Okay? So these are supersaturated solutions. And I'm going to show you on the monitor here. I'll do a couple live, and you could do some if you'd like. Now, let me explain. What this is a bag filled with sodium acetate. Sodium acetate loves to make supersaturated solutions based on its structure. Now, this sodium acetate, has more stuff or more solid dissolved than usual. Okay? Let's do this. Let me show you what I mean. Let's bring this down. Let's pretend potassium nitrate is sodium acetate. What I did is I heated it, or they heated it. Then I cooled it. What happens to the solubility? It drops. But because we don't shake the solution much, it stays in solution. Super, you're flying, you're above. Now I'm at room temperature. This much above the line cannot be supported by the water. Any stress on the reaction makes it come out of the solid. So let me put a stress on this. Put a stress on it, and it crystallizes. Why does it crystallize?
What did you do? You just moved the...
Here it is. See it? The little crystal, I'm going to make some noise here. By making a little noise, now noise makes a sound. Sound is a compression wave. You're pushing sound together and it pushes molecules together. This wants to dissolve. This wants to precipitate. I'm way above the line. A little bit of stress. What happens? It comes out of solution. Because of what? There was more stuff that was above the solubility line. Okay, now it's warm. Try some. All you got to do is wiggle. All you got to do is take the little, all you got to do is take the little disc, stress it out, and it crystallizes.
Can I do it?
Why does it crystallize? Because you had more stuff dissolved. Is it ruined? Please leave them. How do I return these back to their state? I heat them so I reach their saturation point again. Please keep these on the table. Your homework is the next ditto. Please complete that.
I just said it too. Instructions.